Maintaining a beautiful, healthy lawn requires significant amounts of time and knowledge. Maintaining grass height and a quality pest and weed management regimen are required for any healthy lawn to be maintained. The goal of R2 Mode 2 is to provide customers with the tools and knowledge they need to maintain a beautiful and healthy lawn with minimal time and effort from the customer. R2 Mode 2 was designed and engineered by Austin Birch and Yuban Nito. R2 Mode 2 will use automation to maintain grass height, control pests, control weeds, and free up valuable time so customers can spend more time enjoying the benefits of their investment instead of maintaining it. According to the National Association of Landscape Professionals, the NALP, 78% of U.S. adults own homes that require lawn maintenance. Based on a 2016 survey conducted by the NALP, 7 in 10 Americans with a lawn admitted that their landscape capabilities could improve. Target customers are homeowners throughout the United States who lack the knowledge to improve their lawns, or those homeowners who would rather spend the time spent landscaping doing the things that they enjoy. Indirect customers who are also impacted by this problem include homeowner associations, landscape professionals, and Department of Parks and Recreation. So the design requirements for R2 Mode 2 is that the design must be able to maintain a grass height between 1 and 4 inches. The design must be able to control pests with a success rate of 75% per treatment. The design must be able to control weeds with a success rate of at least 75% per treatment. The design must be able to maintain lawns with minimal customer involvement after a 2 to 4 hour setup. The robot workforce designed in R2 Mode 2 will be 4 separate robots in a central hub. The foreman will remove obstacles from lawns and will be designed by Yuban Nito. The cutter will maintain grass height and will be designed by Austin Birch. The sprayer will control weeds and will be designed by Emma King. The spreader will control pests and will be designed by Nadine Eskandar.
Good day, my name is Iban Nieto. I'm part of the Group 17 supporting the R2 Mode 2 design. Within the R2 Mode 2 design, I am particularly responsible for the foreman. The general concept of this foreman robot is it's setting the conditions for the remainder of our robotic components. How do we do this? So, for example, let's say you're using a push mower in your yard, you suddenly hear a rock or a stick kind of mess your lawnmower up. So the idea behind this particular subset system was that we want to set the conditions. We want to make sure that your equipment is protected, but also that your yard is prepared for mowing of your grass or use of any sort of chemicals to kill weeds, etc. So the foreman is the heavy lifter. So the design of the foreman allows it to utilize its limbs, its robotic limbs, to pick up, lift, and store unnecessary items or foreign objects within its body, and then continue to carry it until its weight capacity. Once it reaches weight capacity, the robot will trigger the owner via an app through Signal that it's reached its maximum capacity. At this point, the trigger for the robot will be to initiate movement back to the central hub or to a predetermined location depending on the owner's direction. And the owner can dictate how far or exactly specifically where this individual robot will go. The owner will then go to this particular robot, dispose of said foreign items, and then the robot will re-engage and continue its operations on the designated route or specific area of the yard. Within this robot, we have its circuitry. Foreman's circuitry is composed of the following components within its physical hardware. You have flex sensors, five which identify the 5 fingers of one hand of the robot, or robotic limb, and another set that you won't see identified within this circuitry. But the idea is that you have 10 flex sensors to control each individual finger of the robot. Additionally, microservos to then control also the ability to move, apply pressure, and lift of the foreign objects that the foreman will encounter. You're probably asking, how will this robot know when to stop, go, identify foreign objects? Well, within the circuitry, you have the ultrasonic sensors. These ultrasonic sensors will be dependent on how you write your code, will determine the distance away from that object, and either one will increase speed or continue it on its path without being interrupted, or 3, halt and conduct operations, which would be picking up of the foreign object and storing it away within its body. How does this robot move around? Well, you have 4 hobby gear motors, 2 for the left and 2 for the right side, and these are routed through the L2 or the H-bridge motor. Through this and through the combination of the Arduino Uno, communications will happen back and forth dependent on the sensor. The sensor will then trigger the speed, whether it stops or continues its path, or whether a left side stops and the right side continues to turn left, or vice versa. All these communications are happening through this circuitry, and it's all interconnected to deliver to you, the end user, the ability to, 1, have a autonomous robot that can self-identify obstacles, increase, decrease speed, apply the ability to utilize its limbs independently to pick up items, foreign objects, which are then powered through a 9-volt battery. Depending on the size of your yard, or let's say you want a larger landscaping or foreman robot, the circuitry may be increased through additional hardware systems. But essentially, these are the essential components of the foreman robot. So, how do you develop this language of being able to have your robot or design understand what you're trying to do? Utilize the coding language of C++. So, what happens here? I specifically use the Tinkercad code option. My task was, how do I identify what each finger means? What pin is it connected to? And then based on these pins, how are these pins going to trigger my individual robot to lift, grab, and pick up said foreign objects as my robot is conducting obstacle clearance? So I wanted to identify the finger and which PWM pin it was connected to. Simultaneously, utilizing the ultrasonic sensor and ensuring that the connections are either connected to a specific PWM pin to measure the input and output of the said sensor based on the power it's receiving, as ensuring that it's grounded and also powered. And through these interconnections, the code that we developed further down. So you want to know, like, at what distance will the robot stop or increase speed? So you need an if and else statement. So if X distance, for example, is 30 feet, you set your if distance, front, right, left, etc. Is greater than 30, it's going to continue movement. If it's less than 30, your robot will either do 1 or 2 things. It would avoid said obstacle, or it would halt, try to identify said obstacle for an object within that distance, and based on the distance from a foreign object, it will either continue to trigger to utilize its robotic limbs to pick up said items. Now, how do we control the speed of this robot? So based on the ultrasonic sensor and the distance that it captures, either it would command the robot to continue on its speed. So it could be like something like left motor spin 1, 2, right motor spin 1 and 2 outputs. So full on speed ahead. Or it could trigger left and right motor spin low, which it'll stop your robot if it's low across the board from all left pins and right pins. The halting of this robot will then coincide with identifying the obstacle through the ultrasonic sensor, which then triggers the arms to pick up said foreign items. So as you can see, the code is fairly simple. It's just being able to identify what your limbs are connected to and through what specific hub of input and output it's connected to, and what power is grounded and connected to the components within the breadboard. And so the powering of the robot's movement is through a 9-volt battery. It's particularly for this design. This design would probably give you a robotic design, a fairly small one, but with an increased size, the power required for it will be larger. But this is just for concept and design. Initially, a big thing that I want to identify is identifying which integer variable each individual finger identifies. So identifying these multiple limbs require you to be very particular about which PWM pins they're connected to, and also which side of the L293 pin they are connected to ensure that once your robot identifies through ultrasonic sensor, it stops continuous movement. If it stops, the left side will lift, the right side would lift, etc. So fairly lengthy code, around 145 lines. But at the end of the day, the identification of obstacles, movement, and lifting of said foreign objects being the end state.
Here is the design for the cutter. The cutter will incorporate 2 ultrasonic distance sensors, 3 DC motors, and a 9-volt battery. Here's the code for the cutter. And here is a video of the circuitry. So, as you can see, the motor on the left and right power the wheels. The front ultrasonic distance detector will detect obstacles in the path of the robot. When within 5 inches, the motors will reverse. Then one will run forward, one will run in reverse. That'll turn the robot. Then they will both move forward, and then it will turn the robot again, moving around the obstacle. The ultrasonic distance detector on the left, if it detects an object, the robot will continue to pivot and turn until the obstacle is avoided. Here is the flowchart for the cutter. You can see once it gets the signal to start from the hub, it will scan the environment. It will start its route, and it will begin the loop process. So it will ask, is the route complete? If the answer is no, it will check for battery life. If the battery is not low, it'll ask if the robot is stuck. If the answer is no, it will continue the route and the loop will continue. If the battery is ever low, it will return to the hub until it's charged, and then it will again scan the environment, start the route, and then ask if the route is complete and begin that loop. If the robot is ever stuck, the error indicator will turn on, and when the route is complete, the robot will return to the hub and send a complete signal to the hub. Here's the collective behavior for the swarm. So after the start is initiated by the customer, the hub will power on. It'll ask if the robots are connected. If no, the error indicator will turn on and the hub will power off. If the robots are connected, it'll send out the foreman. It'll have the same loop as a route complete. If no, it'll continue the route. If yes, the foreman will return to the central hub. It'll send out the cutter. Once the route is complete for the cutter, it will return to the hub, send out the spreader. When the route is complete, the spreader will return to the hub, sending out the sprayer. And when the sprayer's route is complete, it will return to the hub and then power off.
So when we're designing this robot, R2 Mode 2 in its overall capacity, we wanted to bring the customer the ability to have flexibility and versatility. What do we mean? Ability to cut grass, ability to conduct obstacle clearance, to conduct pest control, and weed killing. These all are various tasks that one, as a homeowner or individual that takes care of yards, is thinking about, and most of the time isn't fully knowledgeable. So we came with this idea, let's create this multifaceted robotic subcomponent and component system that will give the end user the ability and flexibility to control all these components at will and ensure and set the conditions for time of day and how long they execute said task. Based on all the components, and including labor, paint, etc., the rough estimate of the price of our robot will be around $4,600. Based on this price range, that includes 4 robots to conduct all these tasks. And for that amount of self-autonomous robotic assistance, that's a fairly good price based upon what's out there in the market today. Currently in the market, we have weed killer robots and also yard mowing robots. One example I want to bring to you is the weed robot, which is a costly robot, fairly small in size. It can fit in your palm of your hand, and it's about $350. And its task is to pretty much cut down weeds. Not very practical, could be easily damaged. It's solar powered, so it's a eco-friendly kind of robot. So there's a market out there for the entrance and the utilization of robotics in day-to-day life, i.e. yard work. Another robot that conducts yard work is the yard droid. The yard droid is about $2,000 and is responsible for mowing grass at various lengths of length of grass. It's controlled and maintained within an area through a wire that the customer has to physically lay down in order to ensure that their robot remains within the parameters. And then just to kind of bring another aspect of this, we have the beach cleaning robot, which is called the Bee-Bot, and which this robot is controlled by the end user, constantly controlling it through a remote controller. So as you can see, there's a market out there for robotics in day-to-day yard work. It's a very primitive, very early on in its development processes, but there's definitely a market for it. And there's a wide gap to fill in the knowledge gap of conducting yard work, understanding the capabilities of your robotic systems, and how do we better implement those, understanding cost, bringing the customer durability, flexibility, and just the ability to have free time back and really be able to do hobbies, etc., versus having to push a lawnmower or remotely control the robot throughout the whole entire rotation of its task. So bottom line, all the robots that are out there right now, most of them are fairly expensive by quantity. So it can run you from $350 for one small robot to almost $10,000 based upon what capability and what size of robot you're looking for. So with R2 Mode 2, we want to bring you the ability to have the freedom to conduct daily yard work without having to worry about controlling a robot because it'll be self-autonomous and then basically controlled by a GPS guided system within each robot's circuitry and components. That would allow you to not worry about your system capabilities, etc. In summary, I want to bring to you the lessons we learned throughout this project design process. At the end of the day, any project that you begin to think about, you have an original idea and design for. Um, Furthermore, teamwork is paramount to the success of a project. And most of the time, a lot of design processes initiate with a team wanting a design to be a certain way, or look a certain way. But what you have to keep in mind this throughout the entire process is, what does your end user want? Or what specifically, what do they need? And how can you support that need? I'll say all that to say this. Flexibility is paramount to the engineering design process. And that was fairly apparent through our experience over the past few weeks, coming up with ideas, going back and forth, what works, what doesn't work, and then really taking, at the end of the day, what does the end user need? And we really focus on that. And once we focus on that, we were able to streamline our thought processes and really create these independent designs that worked in unison. Lessons that we want to take forward as well is collaboration is only successful with organized planning, development, and execution timeline. So if you plan, you develop, and you execute according to your timeline, a Gantt chart, for example, there's accountability to maintain deliverables on time and keep you on track to a successful design project. And then as a team member, no matter where you work, what you do, there will be a point where you have to carry the load or help a little bit more in certain areas. This could be due to knowledge gaps, could be to inability to fully understand or grasp a concept, and so you have to be flexible enough to understand that and then carry the project forward. It's about teamwork. I will say, as a team, what we would do differently is better management of our time project. The most difficult thing was different time zones across the U.S., adapting to day-to-day life. Individuals would be in school, working, or family engagements. A lot of responsibilities that were multiple deciding factors that made the collaboration aspect of coming together as one very difficult. Some individuals work 12 hours, some individuals work 8 hours, some individuals work third shift. Very complex environment to work in versus having to work with someone that you're in class with, or that you work with in a occupation that you share an office with, that you can see every day. So definitely a better approach to the time management and conversations early on before starting the project are paramount. And one of the lessons that we learned that we would do differently in the future. And of course, not only restricting yourself within your team to think about ideas and like self-evaluate, but also seeking out peer knowledge, peer critique, maybe reaching out to professors, putting out draft or prototype ideas or designs, or just processes to get feedback. Better utilization of that asset and resource would have made our project more palatable along our process. Finally, during this presentation, we brought you through our engineering design process by focusing on the customer's needs and how that would benefit our customers. Furthermore, along our process, we evaluated various data points from cost, durability, versatility, accuracy that our final R2-Mo2 design would capture. We encountered multiple branches throughout our planning, our design process, that really made us rethink a lot of our approaches and how we created certain designs and certain features that we wanted within our design. Finally, we presented you with a collaborative concept of how each of its individual subcomponent will work together to communicate internally to then deliver the customer the best experience within landscaping. Consequently, bringing the customers a happy experience and more free time to do with their day what they choose to do. And then finally, understanding that the market out there today is vast. There's a lot of options, a lot of robotic companies, a lot of robotic approaches to day-to-day life. But at the end of the day, the end goal is to meet the customer's needs. And each organization approaches this problem set in a different manner. But what is to be true is that the end user should always be kept on top of mind and the main focus of your design process or project. And so today, R2Motu brings you a fairly affordable price for the amount of self-autonomous robots that you'll have to conduct your yard work compared to a market robotic yard product out there today, which can run you from $350 for one individual robot to up to $2,000 based upon your needs. And it's really a gamble, and it's really user preference based upon which avenue or approach you seek to pursue. But at the end of the day, R2Motu brings you flexibility, adaptability, and versatility to your yard work. We bring you weed killers, we bring you pest control, we bring you lawn care, and we bring you obstacle reduction. And with that being said, that's why we believe that R2Motu is the best option for the market.